Here we're going to look at question 7 from section 2 of the ENGAA 2018 paper. In this question, we're told we have a tennis ball moving at 30 meters per second with a kinetic energy of 27 joules. We're then told that our tennis ball is hit elastically by a tennis racket, which applies a variable force to our tennis ball, shown in this force time diagram here. After being hit by the racket, the ball moves away in the opposite direction, and the question asks us, at what speed does the ball leave the racket? If you would like to have a go answering this question yourself, please pause the video now, otherwise let's have a go at it. Now with this question, the first thing we're probably going to do is have a bit of a look at our graph and see what it's trying to tell us. So it's a force time graph, so are there any topics we can think of which are going to relate these two variables? So hopefully we can find some physical meaning from our graph. Well, there is a topic which connects the two, and that is impulse. So what is impulse? Well, impulse is given by the magnitude of a force multiplied by the time that the force is applied for, and this impulse is equal to the change in momentum of an object, or its mass, multiplied by its change in velocity. So straight away, this should probably look a bit useful because we've got a change in velocity there, which is what we're being asked about. And here we have the force multiplied by the time that the force is found across. So the impulse supplied to our tennis ball is going to be given by the area under our graph. Now thankfully the people who came up with this question were quite nice. They made our graph triangular, so it's going to be quite easy to find the area underneath it. How will we find the area underneath it then? Well, it's just going to be a half multiplied by the base of 4 milliseconds, taking care to note of the units, multiplied by its height of 1,500 newtons, Then just by working this through, we find that the impulse is equal to 3 newton seconds. Well, now that we've got the impulse, we can consider the rest of our equation. So we want to try and find our change in velocity, but we still don't have the mass of our equation, of our tennis ball, So how could we find this? Well, how about we go back to some more of the information we were given in this question. The velocity of the tennis ball, right before it collides with the tennis racket, and its kinetic energy before the collision. Now, you might straight away be thinking that from this we can find the mass of our tennis ball. And that's because the kinetic energy is given by a half of the mass of our tennis ball multiplied by its velocity squared. So we do have mass in this equation, and we know all of the other variables. So we can rearrange to get that the mass is going to equal to 2 times the kinetic energy, 27 joules, divided by the velocity squared, which is going to be 30 meters per second, all squared. Now we could try and work this through and get a numerical value, but let's just leave it as it is for now, in the hope that when we substitute it into this equation later on, it's going to be some variables which are going to cancel out, or some factors, that might cancel out. Now that we have our impulse and our mass, let's substitute these two variables in to get our expression becoming this, which we can rearrange for our delta V to get this expression here. So 3 times 30 squared divided by 2 times 27. Now this looks quite horrible, but let's try and think of some things which will cancel out. So we know that our 3 is going to cancel out with a 3 in the 27, since 27 is just 3 cubed. So that's just going to leave a 9 on the bottom, and 30 squared isn't too difficult, it's just going to be 900. So delta V is equal to 900 divided by 2 times 9, and obviously our 9 is just going to cancel with the 900, giving us 100 divided by 2, which is just 50 meters per second. But we're not quite done yet, because this is a delta V, this is the change in velocity of our tennis ball. So if our ball is originally going at 30 meters per second in one direction, and then the velocity changes by 50 meters per second in the other direction, our tennis ball is going to be moving away at 20 meters per second in the opposite direction. So this answer corresponds with answer A given in the question.